All right. So most of you will know what I'm talking about because you were on the mission. So if you don't like something, you've got to be introverted about that as well. Persephone was a planetary mission concept study, so PMCS, funded by NASA in order to determine really what the cost would be to go back to the Pluto system. So I was the PI, Stuart Robbins, who was the DPI, and the ACE lead was Carl Philhauer, who is at APL, but I've never actually met because the whole thing was done during COVID. And so instead of coming out here for the ACE runs, it was all done remotely. And so we had lots and lots of time on Zoom with the engineering staff at APL, but never got to meet them. And that was a really tricky thing, actually, about the Persephone PMCS, was that we got funded right as I went on maternity leave, which dropped Stuart in it pretty heavily. So thank you, Stuart, for picking up the reins and running with it so well for the first month or two. And then it was all COVID. So we had lots and lots of telecons instead of face-to-face meetings. And, we were all getting used to working from home. And my eldest at the time was very little. And she would run into meetings and everyone was very gracious as she disturbed the meetings. And so, but I think it came out of, we still got something that I think was really valuable to the community. And it was really funny going back and reading the paper and looking over the slides, thinking about why we made the decisions we did. And just sort of reliving what that experience was like. So this was a fun thing to think about again. So thank you. It's a big mission. We sort of talked ourselves into probably flying everything and including the kitchen sink, which meant that the end result was probably too big, as you'll go on to see. But I think that process in itself can be incredibly useful because you see that a mission that big is feasible. It did close in the ACE run. So we did have a mission that, if NASA was to pump in the money, could have flown. And also it showed the type of science you could do with different types of instrument that have never got to Pluto before. So I think that in itself is incredibly useful. So, all right. So our main science goals were really, we had three. So the first one was to think about what Pluto's subsurface would look like. With the mission would go into orbit in the Pluto system, we would have good gravity data. We also had an ice penetrating radar, as I'll go on to talk about. So to try and understand what's going on beneath Pluto. And we've been hearing so much that, the New Horizons data gave us lots of good insights into Pluto, but there's still lots of questions that are open. And really, some of them will only ever get resolved if we go back to the system. The second one was about how the evolution of surfaces happened. Not only would we be going back sort of 50 years after New Horizons flew by, so that gives you a big delta timeline, but also looking as we understand more about volatile transport, we understand more about the volatiles that are on the surface, how might, that Pluto-Charon communication work, but how might that change as we go forward in time, but then looking backwards, how would it have changed, over the last few million years? And then the final one was thinking about the diversity of the Kuiper Belt. It's not just a mission to the Pluto system, as I'll go on to talk about, but really to better understand the Kuiper Belt and its constituents. So this is a plot showing the spectral slopes of Arrokoth, comparing them to different types of KBOs and other small bodies. And this is just a sort of, it's fun to think about Arrokoth as well. But it was just to kind of help paint the picture of contextualizing the Kuiper Belt a little bit further. So we're just going to give you some broad brushstrokes. There's a lot to talk about. And the paper came out, I think, in 2022. So there is or 21, there's a paper on it anyway. And so the details can all be found in that PSJ article. But the launch was on a really big rocket, right? So you want to go to Pluto. It was an SLS Block 2 with a Centaur kick stage. So the biggest rocket that we could get within the confines of the PMCS core. We had electronic propulsion. We needed lots and lots of xenon. And then 5 next-gen RTGs, which is a big, big number, right? One is a bit of a tough call. 2, all right, then, and by the time you get to 5, it becomes tricky. And there were lots of decisions that sort of scope slips and things that happen along the way. And the big problem is that it takes a long time and your power's degrading. And so to get the power in order, especially if you want to take ice penetrating radar, you need to take a lot of RTGs. And I think one of the things that came out of this was a real need for that technology development to continue. If you want to explore the outer solar system, having next gen RTGs or improved RTGs was certainly required. And then finally, we had 3 mission phases. So the cruise to Pluto, a Pluto tour, which would last 1.3 Earth years, and then an extended mission tour, which is a little bit unusual to include, but we wanted to include it because we wanted to know how much xenon, how much propellant we would need in order to go and visit another KBO. Like, would it be within what you would normally just have as an error bar, right? Or what would that look like? So we included that in the work that we did. The payload is really, like I say, everything and including the kitchen sink. So we have a pan and color imager, and we based that on the Europa Clipper ice, and then a low light camera. So it was like the WAC, but it had a slightly different aperture so that we could view the South Pole of Pluto. So by the time we went back, Pluto's South Pole would still have been in darkness. So taking a camera that would enable us to see Pluto's southern hemisphere in Charon shine, say that quickly after a beer, was required. A UV spectrometer, because we know how great Alice did on New Horizons, but we baselined and a near IR spectrometer, but this time we baselined the Lucy one because it goes out to slightly longer wavelengths. And again, if you could get, I think it goes out to 3.1, Will probably correct me if I'm wrong. And even extending that out a little bit further would be great. Thermal IR, an RV spec, mass spectrometer, an altimeter and ice penetrating radar, I think would be really cool. And then a magnetometer and a plasma wind instrument. So really, really a lot of good science. But I think that, again, not necessarily that we would expect a final mission to fly all of these, but it was really interesting just to explore the space, that what they could contribute and what kind of questions they could help address. So this was our spacecraft design. As I said, it closed. It's very large. It sort of looks a little like New Horizons, but it has this massive yellow xenon tank at the bottom with its 5 RTGs. We have there's a payload deck, and then we have 2 antennas, one for the ice penetrating radar and another for the mag boom. Launch windows. So this is, as you can see, launch date versus time of flight, and the colors are the arrival speeds. We needed to get there really 6 kilometers per second was ideal. 8 was tolerable. And so this is showing the windows where we could get there. So you can sort of see, if you can't launch by 2032, then you immediately have a 10-year launch penalty. It takes you, if you miss that Jupiter gravity assist, it's going to take you an extra 10 years until it gets into about 2040s, and then it comes back around again. This was the trajectory. So you can see X is just distance from Earth, Y is the distance in the ecliptic, and then Z is distance out of the ecliptic. And we thought a little bit about whether we could do a KBO flyby en route. Already it was going to take us something like 26 years to get to Pluto to arrive at the sort of speeds where you can get into the system. We decided to take a hit of adding an extra year to that cruise time so we could do a KBO encounter en route, like 26 years versus 27, but with a KBO, like it seemed like a bit of a no-brainer to include that. If you can do 26, you can do 27. And that got us to Pluto. So as you can tell, this is a long mission. We did quite a lot of statistical modeling, and that was led by JJ Cavallard, looking at what sort of objects this would be, with the understanding that there was a lot of surveys coming online, right? So there's LSST and Vera Rubin and all these things. So it wasn't that we were necessarily going to visit a known KBO, but we expected there to be a KBO of a certain size available to us if we had that sort of delta V. And then the Pluto tour. So a bit like Cassini used Titan to leverage, to change its orbit, we were able to use Charon. And so we ended up with some really interesting tours. And I think this, again, is a piece of work that would be of use to the community. So in each of these, I'll just talk about what you're seeing. So top left is if you're looking down on the Pluto system, what the tour would look like. And so the dashed lines indicate the orbits of the small satellites, and Pluto's in the center. And then the bottom one, so the left bottom plot, is then looking at the XYZ, so you can see how out of plane they are. On the right-hand side, you've got 2 ground tracks. Top is Pluto, bottom is Charon, and the color indicates the altitude. And these are really unusual, but very, very stable orbits. And so you could actually stay in these without burning much fuel at all, and get additional coverage if you wanted to. And so we separated them into high and low latitude coverage. As you can see here, this is the high latitude one. We have 2 flavors of that. So this is the second one. And each of one gives you different observing geometries for the different instrument suites. So those are our high latitudes, and then our low latitude orbits, where you can see the distance out of plane is a lot smaller. So these would be very good for remote sensing. And that's the fourth one. So to give you an idea of what sort of coverage you would get, this is the NAC coverage that we would find. We've got in the paper plots for all of the instruments, but the NAC's always fun. So obviously we didn't really look at the South Polar because that's dark and you can't really see anything in the NAC if you don't have that reflected sunlight. But the average is about 8 kilometers per pixel, and I appreciate this is hard to see. But to contextualize that, this is Pluto, if you haven't met it before. And 80 meters per pixel is this sort of resolution. So this mission, if it had flown, would be able to image the whole of Pluto at this sort of resolution. That should be phenomenal. We covered a range of emission angles and phase angles and all the sort of good things that you would want from various aspects of looking at craters and looking at thermal and all the fun constraints that you have. Is there a question? Okay. And then finally, in terms of coverage, the WAC, so this is the low light camera. We would focus on, of course, the southern hemisphere. The resolution here is about an order of magnitude worse, but hey, we get to see what the South Pole's like, which is awesome. As I said, we talked about the extended mission. We thought about the extended mission a little bit, and this plot shows, oh, sorry, it's got a bit. So on the bottom part is the transfer time, so how long it would take you to get there after Pluto in terms of years. Pluto distance, so how far out, and that's 5, 10, 18. I don't quite know why the scale got mucked up. And then each one of those lines is for different amounts of fuel. So if you want to go a long way from Pluto incredibly quickly, you're going to burn the most fuel, right? So, but this was a useful plot in terms of thinking about that trade space. And we reserved 250 kilos for the post-Pluto flyby. And we found that there was a bunch of targets that we knew of that we could get to. Depending on how long you didn't mind waiting, you ended up with different solutions, but these were all very viable. Or we thought with the surveys, it was statistically likely that we'd be able to see 150 kilometer KBO within 8 years. That was Jay's work. So to summarize, that we ended up with a long cruise, so 27 years to get there, and then a 3-year cruise around Pluto, and then a possible extended mission where, depending on how long you're willing to wait, so 125, you could see probably 125 known object could be reached within 13 to 7 years, depending on exactly when you got there. And at the bottom, there's a 600 kilometer object that you could reach within 20 years. So we're talking a long wait, but for some pretty cool stuff. So to conclude, our mission closed. One of the things I didn't really talk about was the cost, and that is on this slide, $3 billion. It's quite a bit more than just back of the sofa change in FY25 dollars, excluding all the launch vehicle costs. And so between 5 RTGs and $3 billion, it was a big ask. But I think there's lots of things that came out of this that are incredibly useful. And I think some of the tours that we did, some of the statistical work we did will be useful for future missions, thinking about how to get back to Pluto. But we did show that it's possible, and you can take everything, including the kitchen sink, back to Pluto if you can just get enough money out of NASA. All right, thanks. And with that, I'll take some questions.
Thank you, Kyler. That was a great overview. Rapid fire, but good. Kirby.
Yeah, very cool. I'm really curious, and maybe this is a Ralph question, what the plutonium-238 story is, and if there's enough for 5 RTGs.
There's not.
Okay.
Yeah. By the time you get to 2 RTGs, it sort of doesn't matter if it's 2 or 5 in terms of the plutonium, because there's not enough. There are some of the next gen RTGs that I know the University of Leicester are working on require different levels of plutonium. So that's part of the problem, right? I think the whole tech demo, the tech requirements for tech improvement was a large part of what came out of this. And so I think having access to plutonium is actually the way that we get back to the outer solar system. And we've been proposing missions actually through ESA, and it was quite funny to email people at NASA being like, do you have any plutonium I can have? And they didn't say no, which was quite an interesting email thread. I didn't think I would ever email people for nuclear material and not be told no. So I think it's an interesting conversation. But I think there's a lot around technology improvement and instrument development that needs to be done in order to go back and do it well.
Not to belabor or get out of scope, but is americium-241 ever a possibility for these sort of next-gen RTGs?
I don't know. I'm sorry. I don't remember. We did look at it a lot at the time, but my memory's bad. Sorry.
All
there
right.
we go.
Thanks, Ralph.
Thank you. Thanks.
Thanks, Carly.
Oh.
Oh.
No, no. You
well-
catch me later.
Yeah, unfortunately, we are getting close to the end of the time. We have like 10 seconds left. So, okay. Thank you, though.